Derives theorem. This is something which you'll definitely see in an exam, I'd imagine. It's a very typical sort of question. Something which you should definitely be able to do. Okay, so we're going to use Derives theorem, which is basically a way of doing the powers of complex numbers. And again, obviously, we're dealing with a length and an angle, so we want to be able to put our complex number into polar form before we start playing around with it. So the example I'm going to do here is to find the fourth roots of 16. So that means we're trying to solve z to the power of 4 equals 16. Okay, so it's a fourth root thing. And you'd expect z to the power of 4 to have 4 solutions. Like a quadratic has 2 solutions, a cubic has 3. You'd expect this to have 4 solutions. And if you just get your calculator, so if you rearrange this the way you've done it previously, you go z is the fourth root of 16, or 16 to the power of a quarter. And if you get your calculator to do that, it will tell you that the answer is 2, which is only one solution. And it won't surprise you there's another solution of negative 2, just like when you do the square root of something, you have plus or minus. But there should be 2 other solutions, and they turn out to be, in this case, purely imaginary, but there could be a mix of real and imaginary, i.e. complex. So the question is, how do we get the fourth roots? And the answer is by using de Moivre's theorem, and we need to have our complex number in polar form. Okay, so before we can do this, we need to get it into polar form. So we need 16 in polar form. So if we consider a graph, a Argand diagram with real and imaginary, then 16 is going to be down here somewhere. In polar form, that length of 16 angle is 0. So the number that we're going to be looking at is 16 cis 0. Now, as I've talked about previously, the 0 angle could equally well be 2 pi or 4 pi, etc. So this is actually 0 plus some versions of 2 pi. So 2 pi, 4 pi, 6 pi. So k starts at 0, which gives us just cis of 0. And then when k is 1, we'll have 16 cis 2 pi. When k is 2, we'll have 16 cis 4 pi, etc. So we need to be able to get an infinite number of solutions. And then all we're going to say is that if z equals 16 to the power of a quarter, that's equal to 16 cis, in this case 0 plus, so just 2 pi k to the power of a quarter. And then we use de Moivre's theorem. So de Moivre's theorem tells us that it's the length to the power, 16 to the power of a quarter, cis, and then we multiply the angle. So we end up with n times theta. So n is a quarter here, theta is 2 pi k, so a quarter of 2 pi k is the same as pi k upon 2. Okay, so that gives us the numbers that we're working with. 16 to the power of a quarter, it just wants the size of that, so that's 2. And then we have cis pi k on 2. And we need 4 solutions, so we're going to go for k equals 0, 1, 2, and 3 to give our 4 solutions. Okay, so if k equals 0, so the first solution is when k equals 0, z equals 2, cis is cos, k is 0, so the whole thing's angle is going to be 0, plus I sine of 0. Sine of 0 is 0, so that goes away. Cos of 0 is 1, and we're just left with 2. So one of the solutions is 2, which is kind of nice. If k equals 1, then z equals 2 lots of cos. If k equals 1, which angle is just pi over 2, plus I sine pi over 2. Cos of pi over 2 is 0, sine of pi over 2 is 1, so we just get 2i. If k equals 2, then z equals 2 lots of cos. K equals 2, so it's got pi as the angle, plus I sine pi. Cosine of pi is negative 1, sine of pi is 0, so you end up with negative 2. And if k equals 3, 2 lots of cos 3 pi over 2, because k is now 3, so we've got 3 pi over 2, plus I sine 3 pi over 2. cos of 3 pi over 2 is 0, sine of 3 pi over 2 is negative 1, so it gives us negative 2i. And if you did carry on and do k equals 4, you'd find you come back to 2 again. Okay, so this gives us 4 solutions. So one solution is at 2, the next solution is at 2i, the next one's at negative 2, and then at negative 2i. So you get 4 solutions equally spaced around an Argand diagram. And it'll always be the case. It'll be, well, it won't always be 4, but it'll always be evenly spaced around the Argand diagram. And using de Moivre's theorem is the way that you can solve exponential equations with complex numbers.